Hi friends, welcome to the next session of the subject Engineering Mathematics. In this session, we continue classroom workbook questions. Now let us start from question number 15. Just go through your handout. Let us start from question number 15. The inverse of the matrix 0, 1, 0, 0, 0, 1, 1, 0, 0. So they asked the inverse of a 3 by 3 matrix. Suppose if it is a 2 by 2 matrix, say for example A, B, C, D entries, we have a direct formula. A inverse is 1 by AD minus BC into D minus B minus CA. But as it is a 3 by 3 matrix, we need to find cofactors of 9 elements. What is the formula for inverse of matrix? 1 by det A into adjoint A. What is adjoint? Let me write out the formula. A inverse formula is 1 by det A times adjoint A. So this is nothing but 1 by det A times, what is adjoint of A? This is a transpose of the cofactor matrix A. That means you need to find cofactors of all these 9 elements. We need to find cofactors of all these 9 elements. But here options are given, so therefore you need not find cofactors of all the 9 elements. In fact, this problem can be solved in 2 different ways, because this is one way is assume that this is A. Let us find the det of A. Now therefore you can expand det value like this, or this is nothing but identity matrix almost, but rows have been exchanged twice, 1 0 0, 0 1 0, 0 0 1. Or you can do like this, det is, I am expanding det value by using last row, 1 into determinant of 1 0 0 1. So its det is 1. Therefore, what is the det of A inverse? Reciprocal of det A. So this is 1. So det A is 1, det of A inverse is 1. Now here let us try to find A inverse by using its det value. Suppose here 4 options are given. If only one option has det value 1, that could be A inverse. Got this point? Here det A is plus 1. Now according to the formula, det of A inverse equal to 1 by det A, the det of A inverse also equal to 1. Now let us try to find determinants of all 4 options. If exactly one option has det value plus 1, then that could be right answer. If multiple options have det value 1, then I need to go in the different approach, right? So that is one way. And second way is, in all the options, try to find a position where all the elements are different. Now let us see in this case, in option A, the first element is 0. Option B, first element 1. Option C, first element 1. Option D, first element 0. Therefore, if you find first element in A inverse, if it is 0, the answer can be either A or D. If the first element in A inverse is 1, the answer is either B or C. Even in this way also, 2 options can be eliminated directly. Now at least let us see in that way. So therefore in this case, det of 1 by det A is 1, det A is 1, therefore this is ACF transpose. Therefore this is nothing but transpose of cofactor matrix. Transpose of cofactor matrix. Now let us find the first element. Therefore this first element is nothing but cofactor of this only, because this is in 1 1 position. Here A11 is 0. Even when you find its cofactor, replace here and transpose this, it doesn't change its equation. So what I am doing is, at first I am trying to find the cofactor of starting element. So therefore cofactor of A11, this is minus 1 whole power 1 plus 1 into determinant of, eliminate this row and this column, you will get this one. So this is 0 1 and this is 0 0. Therefore in this case we are getting answer as minus 1. So let us see the question once again. 0, 1, 0, 0, 0, 1, 1, 0, 0. The cofactor of starting element. Of course, this is its det value is 0. Its det value is 0. Therefore, the first element in A inverse is 0. So we have two different options. In first option, det value, in first option, the first element is 0. Even in the last option, the first element is 0. So the answer is either A or the answer can be either D. Now let us see where you have the difference. Answer is either A or D. In option A, the second element in third row is 1. In option D, the second element in third row is 0. That means let us concentrate on this position. This is nothing but A23. A23. Sorry, this is A32. A32. Therefore, let us try to find second element in third row. Suppose if A32 is 1, then A is right answer. If it is 0, then D is right answer. Therefore, based on finding the cofactor of the starting element, two options are eliminated. Option B is eliminated. Option C is eliminated. So, answer is either A or D. Even if you want to eliminate either A or D, let us try to find 3-2 position element, because A32 is 1 in option A and A32 is 0 in option D. So, therefore, this is A32. But this is in this position. Therefore, this is nothing but, this A32 is nothing but cofactor of A23. Because when you replace cofactor of A23 and when you transpose, it reaches to 3-2 position, because adjoint is a transpose of cofactor matrix. Now what is A23? This element. Third element in the second row. Therefore, this is minus 1 whole power 2 plus 3 into determinant of, eliminate this row and this column, we get this submatrix 0, 1, 0, 0. 0, 1, this is 1, 0. Therefore, this is minus 1 into minus 1, this is plus 1. Therefore, this element is plus 1. Therefore, the answer is A. Right? Let me explain once again. You need not worry about this question. It is very simple. So when they ask you to find the inverse of a 3 by 3 matrix, we have multiple chances. One way is like this. Just find the det of that matrix. Suppose if det equal to K. Now what is the det of A inverse? 1 by K. Now let us find determinants of all options. If only one option has a det value 1 by K, that could be right answer. But it may not be possible in all cases. Suppose if multiple options have det value 1 by K, then it is not so simple to eliminate options. Now in that case, what we need to do is, just you identify a position where all elements are different in all options. Suppose the second element in third row, for example, if the second element in third row is different in all options, that is A32, then you try to find cofactor of A23. Suppose if A23 is different in all options, then try to find the cofactor of A32, because adjoint is a transpose of its cofactor matrix. Why we are using adjoint? The formula for A inverse is 1 by det A times adjoint A. So in this case, what happens is, when I calculate det of this matrix, I am getting 1. So what is the det of A? Det of A inverse, it is 1. Now, but I am following in the different approach. This is one way, but at this moment, I have stopped it. Let us go in the different way. Even I will come back to this point also. So in this case, the formula for A inverse is 1 by det A into adjoint A. But det A is 1, therefore A inverse is ACF transpose. Now let us see. In all options, the first element, at least in B and C, the first element is 1. In option A and D, the first element is 0. Basically, the first element in ACF transpose is cofactor of A11. So this is the first element in first row, 0. So let us find the cofactor of this element. We are getting 0. Now replace that element here, transpose this, it doesn't change its location. Therefore, 0 is the starting elements in A inverse. There are two different options That is A and D, where 0 is the starting element. But in case of option B and C, the starting element is 1. So therefore, according to this calculation, option B and C can be eliminated, right? So answer can be either A or D, right? Now, let us try to find the difference in the location. Now, when you go to second element in the third row, in option A it is 1, in option D it is 0. Therefore, let us try to find this element. But A3, this is in A inverse, second element in C2 position. But before transposing this is nothing but cofactor of A23. So this is the element, third element in second row, this is A23. Therefore, this is nothing but cofactor of A23, this particular element. So find the cofactor of this, you will get 1. Therefore, this element, that means second element in the third row is 1, and that is happening only in option B. Therefore, it is B. This is one way, and even there is another way. Just one simple way is apply the definition. What is the definition of invertible matrix or inverse? Like this. When you multiply A with A inverse, you will get I. See, every matrix, if it has an inverse, it will be exactly 1 only. That is a well-known fact. Therefore, you try to find original matrix with option A, you will get I in this case. So therefore, A is right answer. Multiply original matrix with options. Suppose when you multiply original matrix with option C, if you are getting I, then option C is inverse of that matrix. If it is happening for D, D is right answer. If it is happening for option A is right answer. Just a verification of A into A inverse. Multiply each option with original matrix. If you get I, then that could be right answer. In this case, there will be no chance to get two different inverses, right? So this is the way to get the inverse of matrices from size 3 by 3 onwards. Note this. Now just go through question number 16. Let me read out question number 16. In matrix algebra, A into S equal to A into T. That means A, S, T are matrices of appropriate order. Appropriate order means they are flexible for multiplication. So in matrix algebra, A is equal to AT implies S equal to T only if options symmetric, singular, non-singular, skew symmetric, right? Let us see. The problem is this, A into S equal to A into T. See, from this I must get S equal to T. So A is equal to AT implies S equal to T only if. So that means there is only one occasion where you can cancel A on both sides. Now actually this is very similar to an equation in rhombus. Suppose if I have numbers like this, 2x equal to 2 into y. Just this is matrix equation, this is general algebraic equation, right? Now A is similar on both sides. Here number 2 is similar on both sides. Therefore in this case you will get x equal to y. Why? Because 2x equal to 2y implies x equal to y. We are getting this equation because we are multiplying this equation with 1 by 2. So 1 by 2 into 2x equal to 1 by 2 into 2y. So this implies 1 by 2 into 2 is 1. So 1 into x equal to 1 into y. This implies x equal to y. Therefore here I multiplied this equation with 1 by 2. Basically this 1 by 2 is nothing but multiplicative inverse of 2. This is nothing but multiplicative inverse of 2. Therefore when you are able to multiply inverse of this repeated element, then that element will be cancelled on both sides. Got it? So therefore if you want to cancel a term which is repeated on both sides when the operation is multiplication, be cautious that that must be a non-zero number. Let me tell you one funny incident happened in my life when I was in 7th standard. My mathematics teacher was asked the students like this, prove that 1 equal to 2. So one of my friend proved this like this. He took like this 0 equal to 0. This is clear. And this 0 he wrote like this 1 into 0. This 0 can be represented 2 into 0. So 0 is repeated on both sides, cancel out. Therefore 1 equal to 2. But this is absolutely wrong. Right? Because you cannot cancel 0 on both sides if the operation is dot, because 0 has no inverse. 0 has no multiplicative inverse. Therefore, when the operation is involved on both sides, when the operation is involved on both sides is multiplication, if a quantity repeats on both sides, you cancel out only if it is a non-zero number. Got it? Therefore, this is funny incident. Now, let us come back to this. Hope when you follow this, you can understand very clearly. So, what is my equation? A into S equal to A into T. Just multiply this equation with both sides, A inverse. A inverse into A into S equal to A inverse into AT. So, by associative law, this will be A inverse into A into S equal to A inverse into A into T. This is by associative law. When a matrix is multiplied with its inverse, you will get identity matrix. I into S equal to I into T. I into S equal to S, I into T equal to T. Therefore, from this, we got S equal to T only if it is multiplied with A inverse. See, we can multiply equation with A inverse only when A inverse exists. So, when A inverse exists, only when det A is not equal to 0. Therefore, when det A is not equal to 0, then only I can multiply this equation with A inverse. So, det A not equal to 0 means A is a non-singular matrix. Note down this point. Now let us move to question number 17. Given that A equal to a 3 by 3 matrix 5 0 2 0 3 0 2 0 1. So they were asking inverse of this matrix. Options are given. So here also when options are given, try to identify a location where all elements are different. And you find only that element, you will get the result. You need not find cofactors of all 9 elements, right? Because A inverse is 1 by det A times adjoint A. How to get adjoint? This is a transpose of its cofactor matrix. Therefore, in order to find adjoint of a 3 by 3 matrix, in general, we need to find cofactors of 9 elements. But certainly, when you go for calculation of 9 cofactors, time will be more. So, in order to minimize the time factor, let us try to find an element where the position is different in all cases, in all options. Now, let us see. 1 by 5 is the first element in option C and D. No is. When you calculate first element, if it is 1 by 5, answer can be C or D. If you find first element, if it is 1, answer is A. If it is 5, answer is B. But 1 by 5 is repeated 2 in 2 different options. Now let us go to first element, the third element in the first row. In first option, it is -2. That is, I am concentrating on A13. Third element in the first row. In first option, it is -2. In second option, 2. In third option, 1 by 2. In fourth option, it is -1 by 2. Therefore, this element is different in all options. So, let us try to find this. Before finding this, let me write the formula for A inverse. So here A inverse equal to 1 by det A into adjoint A. Now what is det A? Now in this case, second row contains majority number of zeros. So let us expand det value by using second row. This is 2, 1, 2, 2, 2, 3. The sign is plus. Therefore, det A equal to 3 times det of, eliminate this row and this column. You will get remaining submatrix 5, 2 and 2, 1. So this is 3 into 5 minus 4. So this is 3. So therefore, det A equal to 3. Therefore, A inverse is 1 by det A into adjoint A. So this is 1 by 3 into, this is ACF transpose. Now we know that in the inverse, the third element in the first row is different. So this is nothing but 1 by 3 into this. I need to find this element. This is basically A13. But basically this is in the third element in the first location. After making transpose. But before making transpose, this will be in which position? A31. Therefore, this A13 is nothing but cofactor of A31. Therefore, this A13 equal to cofactor of A31. This is minus 1 whole power 3 plus 1 into determinant of, this is the first element in the third row. Now its cofactor, eliminate this row and this column. You will get this 2 by 2 matrix. So it is 0, 2 and this is 3, 0. Therefore, this is 0 into 0 minus 2 into 3. This is positive. So this is minus 6. Therefore, this A13 is minus 6. So multiply 1 by 3 with a minus 6. Therefore, this result becomes minus 2. Therefore, minus 2 is available in option A. So A is the right option. Note this. I hope this is very clear. Now let us move to question number 18. So given matrix A equal to 4, 2, 1, 3, 6, 3, 4, 7, 2, 1, 0, 1. Then the rank of this matrix is. So they were asking rank of this matrix. Options are 4, 3, 2, 1. Now, what is the size of this matrix? It has 3 rows and 4 columns. The size of this matrix is 3 by 4. So what is the minimum of these two numbers? 3. Therefore, maximum rank of A equal to 3. So maximum rank will be 3. Otherwise it can be 2. Otherwise it can be 1. Otherwise it can be 0. But there is no chance to get rank of this matrix as 0. So only these 3 possibilities are there. Let us try to find whether it has a rank 3 or not. So in this case, this is not a square dimension. One column is x's. So what I will do is, at first I will try to see whether it has a rank 3 or not. First eliminate first column. One column is x's. Whenever number of columns are x's, eliminate those number of columns. So here what I will do is, I eliminate first column at first. I will get one submatrix, call it as A1. Next eliminate second column. Next third column. Next fourth column. So when I eliminate first column, or only second, or only third, or only fourth, I will get 4 submatrices of size 3 by 3. I assume that they are A1, A2, A3, A4. Out of these 4, if at least one has det value not equal to 0, then my rank is 3. Got it? So try to understand this. This is not a square matrix. It is a rectangular matrix. So one column is x's. Whenever there are more number of columns, eliminate those number of columns to make the square dimension, right? So in this case, what I do is, I eliminate at first column 1. I will get A1. Let us see. Here A1. A1 is a submatrix by eliminating only first column. So this is 2, 1, 3, 3, 4, 7, 1, 0, 1. So this is a 3 by 3 submatrix. Now here the data of this matrix is 0 because the reason is 2 plus 1 is 3, 3 plus 4 is 7, 1 plus 0 is 1. That means column 3 equal to column 1 plus column 2. That is a linearly dependence relationship among columns. 2 plus 1 3, 3 plus 4 7, 1 plus 0 is 1. So here one 3 by 3 submatrix has det value 0. It doesn't mean that rank not equal to 3 because there are multiple number of 3 by 3 submatrices in this case. Got it? Therefore, let us move to another 3 by 3 submatrix. Now I eliminate only second column. So therefore I am getting another 2 by 2 submatrix which I call it as A2. So this is 4 1 3, 6 4 7 and this is 2 0 1. This is also a 3 by 3 submatrix. Now let us find data of this matrix. So here this is 4 into this is 4 minus 7, 4 minus 0, this is 4 minus 1 into 6 minus 14 minus 8 plus 3 into this is minus 8. So this is 16 plus 8 minus 24. Here also det value is 0. Now I will go for A3. A3 is a 3 by 3 submatrix by eliminating only third column. Then I will get 4 2 3 6 3 7 2 1 1. Now it is easy to say that its det value is det is 0 because first column is 2 times of this 2 2 4 3 2 6 2 2 4 3 2 6 1 into 2 2. That means column 1 equal to 2 times column 2. Therefore det value is 0. Similarly, when I go for there is a chance, still there is a chance to get rank value 3. Now I will go for last submatrix by eliminating last column. So A4 is a 3 by 3 submatrix by eliminating last column. So it becomes 4 2 1 64 and this is 2 1 0. Here also its det value is 0. The same reason what we had in case 3. So column 1 is 2 times of column 2. Therefore what happened in this case is every 3 by 3 submatrix has det value 0. Write it. All 3 by 3 submatrices have det value 0. Therefore rank not equal to 3. So rank not equal to 3. If rank not equal to 3, there is a chance to get rank value 2. Now in this case, suppose if I start with this noise, now I will go for this. Now I call it as this is A5. This is 3 4 1 0. It is a 2 by 2 submatrix. What is the data of this matrix? 3 into 0 minus 1 into 4. This is minus 4. It is not equal to 0. Therefore there is a 2 by 2 submatrix whose data is not equal to 0. Therefore the rank of this matrix is 2. Note these points. Now let us move to question number 19. What it is? If R equal to some 3 by 3 matrix, then the top row of R inverse. Only they were asking first row, top row. So in this case, there is no chance for verification. Let us see, the matrix is this. R equal to 1 0 minus 1, 2 1 minus 1, 2 3 2. They were asking top row of R inverse. Now even in this case, the first element in first two options is 5. The first element in last two options is 2. So you won't get directly by finding first element. But when you go through second element, In the first option, second element is 6. In second option, minus 3. In third option, 0. In fourth option, it is minus 1. Therefore, second element is different in all options. So let us try to find second element in the first row. Then you can easily get the answer. So the formula for R inverse is 1 by det R in adjoint of R. So this is 1 by det R into, this is RCF transpose, cofactor matrix of R. So this is 1 by det R times, you will get some 3 by 3 matrix. But I want to find only this element. So this is in which position? 1, 2. So this is basically R12, second element in the first row. But basically this is nothing but cofactor of R21, right? So this R12 equal to cofactor of R21. Of course, it has to be divided with 1 by det R. Now let us find the data of this matrix R. Expand by using first row, plus minus plus. So 1 into data of this matrix, 2 plus 3, this is 5, minus 1 into 2 into 3, 6 minus 2, this is 4. So it is 1. Therefore, R inverse equal to RCF transpose directly. Now therefore, in RCF transpose, this is my element R12. So R12 is cofactor of R21. Therefore, cofactor of R21 equal to minus 1 whole power 2 plus 1 into det of R21. This is my R21, first element in the second row. Its cofactor can be evaluated by eliminating the row where 2 is present and by eliminating the column where 2 is available. So consider the next submatrix. Therefore, this is determinant of 0, minus 1, 3, 2. Therefore, this is minus 1 into, this is 3. 0 into 2 minus 1 into 3. So this is minus 3. Therefore, the second element in the first row is minus 3, and that is happening only in second option. Therefore, the answer is B. Now let us move to question number 20. Just go through question number 20. What it is, the maximum value of determinant of all 2 by 2 real symmetric matrices with trace 14. So clearly indicates that matrices are of size 2 by 2. Real matrix. What do you mean by real matrix? If all elements inside the matrix are real numbers, then it is called a real matrix. Symmetric means A equal to A transpose. Trace means sum of diagonal elements. So what we need to consider is, you consider all 2 by 2 real symmetric matrices with trace 14. You may have infinitely many matrices. So you find determinants of all such matrices and tell me the maximum value of maximum det value. That is the question. Really worthwhile question this is. So the question number is 20. So I consider a matrix A. This must be real symmetric matrix. Real symmetric matrix. But the trace of this must be 14. So it is a symmetric matrix. That means A must be equal to A transpose. Now I will take general matrix A like this. This is AB, BC. Since it is a symmetric matrix, A must be same as A transpose. You can easily verify this is a symmetric matrix. A is same as A transpose. B is equal to B. This A and C can be different. So this is a real symmetric matrix. Since I am saying that it is a real, A, B, C are real numbers. So this R represents set of real numbers. Right. Now here trace is 14. What is trace means? Sum of diagonal elements. So this is A plus C equal to 14. Now what is the det of this matrix? A into C minus B into B. This is AC minus B square. Now therefore in this way I can produce infinitely many matrices by changing the values of A, B, C. So by taking different values of A, B, C, I will get infinitely many matrices. So it is not practically possible to find the determinant of infinitely many matrices. Even after that, we need to find its maximum value. So it becomes so complicated. Now let us do not follow by taking examples. Don't assign random values for A, B, C. Just let us try to solve this in more general way. Do not assign any values for A, B, C. What happens when you assign different values for A, B, C? You will get different matrices. How many you will get like that? Infinitely many. So is it practically possible to get the determinants of infinitely many matrices? Certainly not. Therefore, in that case, what you need to do is just don't take random values for A, B, C with the trace 14. Let us get the answer in more general way. Let us see all possible cases. See here, that is AC minus B square. Here if B is negative or B is positive, implies B square is greater than 0. So in this expression, because we want maximum value for det A, suppose if B is negative or B is positive, but B square is positive. So that means we are subtracting, because of this minus, we are subtracting a positive quantity from AC, by which maximum det is not possible. Following? Here B is, if B is either negative or positive, because there are three types of real numbers. Real number can be negative or positive, or it can be 0. No other way. It can be negative or 0 or positive. If B is either negative or positive, in both the cases, B square is positive. And we are subtracting a positive quantity from AC, by which maximum det is not possible. Therefore, in this case, if B negative or B positive, B square is less than 0, implies maximum det is not possible. So to get the maximum det, comma, B could be 0. Therefore, the matrix A is restricted to A0, 0, C. So take B equal to 0, you will get A0, 0, C. Now the det of this matrix is AC. But anyhow, trace is 14. So A plus C is 14. Now let us see, in this case, suppose if it is 100, for example, if it is a minus 86, Because if it is 100, this could be minus 86. Then trace will be 14. But 100 into minus 86 minus 8600. Negative debt we are getting. But still there are some chances to get positive debt value because we want maximum debt. Therefore, in order to get the maximum debt, so take A value positive and C value positive. That is very clear. Now list out one tabular form where possible cases. Now let us see. This is A, this is C, and this is AC. Basically, this is debt value. So suppose if A is 1, C is 13, debt is 13. If this is 2, increase A value, decrease C value. So that sum must be 14. Debt value 24. If it is 3, this is 11, 33. If it is 4, this is 10, this is 40. If it is 5, 9, 45. If it is 6, 8, 48. If it is 7, this is 7, this is 49. Now, when you continue like this, next 8 and 6 will be repeated. But that will be again these cases. 8, 6, 9, 5, 10, 4, 11, 3, 12, 2, 1, 3. Again, those values have been repeated because answer will not change. Same debt values will repeat. Now, out of all these debt values, the maximum debt is 49. That means indirectly, they asked the question, what is the determinant of the matrix 7007? Indirectly, they asked the question, what is the determinant of 7007? So, note these points. So, what is the answer? 49. Hope you understand this question. Highly tricky question. Even we solved this question during chapter 3, that is the differential calculus. In the meanwhile, in the calculus part also, let us try to solve this question by using stationary points, maxima, minima, etc. Right? Now let us move to question number 21. Question number 21. Let m power 4 equal to I, where I is an identity matrix. But m not equal to I, m square not equal to I, and m cube is not equal to I. Then what they were asking, for any natural number k, what is m inverse? So here m is a matrix. But m power 4 is I. I is identity matrix. M not equal to I, m square not equal to I, m cube not equal to I. Then for any natural number k, what is m inverse? So options were different. M power 4k plus 1, m power 4k plus 2, m power 4k plus 3, m power 4k. So let us verify options. Now multiply m with first option. The first option is m power 4k plus 1. So if I multiply first option with m, if I get I, this could be right answer because I am following definition of invertible matrix AB equal to I. If AB equal to I, then this is inverse of A. So multiply option A with m. So in this case, this is m into m power 4k into m. This is m into m power 4 whole power k into m. But m power 4 is I power k is I. So I power k is I, m into I, m. So this is m square but not equal to I. It is given that m square is not equal to I. Therefore, when you multiply m with first option, we are not getting I. Similarly, when you multiply m with second option, m into 4k plus 2, the result is this, m into m power 4 whole power k into m square. Anyhow, this is I, this is m cube not equal to I. Therefore, B also not a right answer. But when you multiply m with third option, m into m power 4k plus 3, this is m into m power 4 whole power k into m cube. This is I. M into m cube is m power 4, this is I. So when you multiply option C with m, you are getting I. Therefore, by definition, M inverse is M power 4k plus 3. So this is simple for just verification of options. What I did is just I multiplied each option with M. When I multiplied option A with M, I am not getting I. When I multiply M with option B, I am not getting I. But when I multiply M with option C, I am getting I. Therefore, this is inverse of this. So therefore, the answer is C. So this is the end of this session. Hope we continue next classroom workbook in the next session. Thank you so much.